In this video, we're gonna learn homogeneous differential equations. But before we head to the real form of differential equation, let's talk about the definition of homogeneous function. So a function of two variables f, x, y is called homogeneous of degree n if for any t that is bigger than 0, f t x t y is equal to t to the n f x y. So this is the definition. Well, it means in order to check that a function is homogeneous of degree n, you have to verify by using this equality. For example, let's say that I have fxy equal to x squared plus y squared. Well, if I want to check that the function f is homogeneous or not, so I have to check by consider f tx comma ty, and then this thing is going to be tx square plus ty square, and then you simplify it so you get t square x square plus t square y square, and then you can pull out t square, and then that will end up with t square times f xy. So you can see from here that you have f tx ty equal to t squared times f xy. So then by definition, f is homogeneous of degree 2, right? Another example, you could have, let's say gxy equal to x cubed times cosine x over y, for example. Then here you're gonna have gtx ty equal to tx cubed cosine tx over ty, and then once you simplify it, so you get t cubed x cubed cosine x over y, and that thing is t cubed times gxy. Well, that means g is homogeneous of degree 3. This is how we check if function f is homogeneous. Alright, now let's move to the definition of homogeneous differential equations. So a first order differential equation in the form mxy dx plus nxy dy equal to 0 is said to be homogeneous if m and n are both homogeneous functions of the same degree. So once you have a differential equation, well, you have to simplify to the standard form m dx plus n dy equal to 0. Once you simplify into this form, then it is called homogeneous if m and n are both homogeneous. For example, let's take a look at let's say dy by dx equal to y squared minus x squared over xy. So I want to check if this differential equation is homogeneous. So what I'm gonna do is I have to simplify this thing. So it will be xy dy equal to y squared minus x squared dx. And then after that, well, I can simplify more, so I get x squared minus y squared dx plus xy dy equal to 0. So this is now in the standard form, right? And then from here we can see that my function m is x squared minus y squared, and my function n is xy. Well, in order to be a homogeneous differential equation, I have to make sure that m and n are both homogeneous. So I'm gonna show it here. So let's compute mtx ty. So this thing is tx square minus ty square, and then that thing is t square x square minus t square y square, and then that will be t square times x square minus y square, which come back to t square times mxy. So mxy is homogeneous of degree 2. And then let's do ntx ty. This is equal to tx times ty. This thing is t square times xy, so it's come back to t square times nxy. So this thing is also homogeneous of degree 2. Well, because both m and n are homogeneous of the same degree, so we conclude that dy by dx equal to y square minus x square over xy. This differential equation is homogeneous. Now let's talk about the idea how to solve homogeneous differential equations. So first, I'm going to introduce you to properties. Properties number 1. If f is homogeneous of degree m and g is homogeneous of degree n, then f over g is also homogeneous of degree m minus n. That is property number 1. Property number 2, if I have a function f that is homogeneous of degree 0, then f is a function of y over x. I'm not going to prove these two properties, but we are going to use them to build up the idea how to solve homogeneous differential equation. So let's take a step back to homogeneous differential equation. So we have mxy dx plus nxy dy equal to 0. If I simplify this thing, what I'm gonna get is dy by dx equal to minus mxy over nxy. And now take a look at the right hand side here. On the right hand side, I have mxy over nxy. So we know that m is homogeneous because this is homogeneous differential equation. And then we also know that n is also homogeneous and they have the same degree. So if I do the ratio m over n, by property number 1, this thing must be homogeneous of degree 0, right? By property number 1, I can say that this thing must be homogeneous of degree 0. Nice. And then by property number 2, because this thing m over n is homogeneous of degree 0, it can be rewritten as a function of y over x, right? And that thing, well, I can name it. Let's say this thing, the name of the function is r. So this is r y over x. So now we have a differential equation dy by dx equal to a function of y over x. So the idea of homogeneous differential equation is we are going to do a substitution. So let's say that I'm going to make a substitution here. So I'm going to use, because this is a function of y over x, So what I'm gonna do is I am going to let v equal to y over x. So we're gonna do, let's do a substitution. So we're gonna let y equal to v times x, or v equal to y over x. So this is the same thing with y equal to v times x. And once we set this thing, so if I differentiate with respect to x, so I'm gonna get dy by dx equal to, on the right hand side I have to use product rule here, so it's going to be v dx by dx plus x dv by dx, and this thing is going to be v plus x dv by dx. So I can use this thing that I highlight in yellow here. So I'm gonna replace it back to the differential equation. So what I'm gonna get is, I'm gonna get v plus x dv by dx equal to r v here. So what I'm gonna do here is I am going to simplify it. So that will be x multiplied dv by dx equal to rv minus v, and then after that I can simplify more, so that will give me dv over rv minus v equal to dx over x. So this thing is a separable equations. So the idea of homogeneous differential equation is we're gonna make a substitution, y equal to vx, and then after that the differential equation will turn to separable equation, and then we can solve. To sum up, this is how we solve homogeneous differential equation. First, you simplify it. Simplify until you get mxy dx plus nxy dy equal to 0. This is the standard form of homogeneous differential equation. Once you have m and n here, so you have to check first. So number 2, show that m and n are homogeneous of degree, of the same degree, can be anything, so of the same degree. Alright, next, once you show that m and n are both homogeneous of the same degree, so you know that this is homogeneous differential equation, then you make a substitution. So let y equal to v times x, then what are you going to have is dy equal to v dx plus x dv. This is by product rule, but you just trying to write it in the form of differential. So you have dy equal to v dx plus x dv. And then number 4, replace dy into the original differential equation. Then the original equation, differential equation, will turn to a separable equation. Separable equation in terms of x and v. Well, we will show you how to do it in the next example. Now let's take a look at example 5. Find a general solution of this differential equation dy by dx equal to y times x minus y over x squared. So you can see that I changed the question from the lecture note. There's nothing wrong with that question. It is just too long. So we're gonna start by the simple example first. So this example, once you look at the differential equation, you can see that this is not separable because you cannot separate x minus y here, right? So this is for sure not a separable equation. So let's start by simplify it to the standard form. I am going to get x squared times dy equal to y times x minus y dx, right? This is by, you can say, cross multiplication. And then after that, well, I am going to get y times x minus y dx minus x squared dy equal to 0. And now from here, you can see that my mxy is going to be y times x minus y, and my nxy, it is minus x squared. So we're going to check here if m and n are homogeneous of the same degree. So let's do mtx ty. This is ty times tx minus ty. And once you do the algebra, so you're going to get t squared times mxy. So this is homogeneous of degree 2. And then also if you do ntx ty, this is going to be minus tx in parentheses square, and that will give you t squared times nxy. So this is also homogeneous of degree 2. So this is actually a homogeneous differential equation. So now once you know that this is a homogeneous differential equation, you have to do a substitution. So let's y equal to v times x. Then what you have is dy equal to v dx plus x dv, right? And next, I am going to replace my dy here into the original equation. So once I replace dy into the original equation, then what I should get is a separable equation in terms of x and v. Let's do it. So what I'm going to get is, so from this equation that I start here, I'm going to replace y by vx, and I'm going to replace dy by v dx plus x dv. So what I get is vx x minus vx dx minus x squared times v dx plus x dv equal to 0. What I'm going to do is I'm going to expand it. So I'm going to get v times x squared dx minus v squared x squared dx minus x squared v dx, and then minus x cubed dv equal to 0. And then now you can see that vx squared dx and this term, they cancel out. So actually what you have left is going to be minus x cubed dv equal to v squared times x squared dx. I love to keep dv on the left hand side. And then this is now a separable equation. So you have to move everything in terms of v to the left hand side, and then move everything in terms of x to the right hand side. So now you're gonna get negative 1 over v squared dv equal to 1 over x dx. And now you're ready to integrate on both sides. So integrate it, and then now you get on the left, you get 1 over v, right? Because integrate 1 over v squared is negative 1 over v, and then with negative side you get 1 over v. On the right hand side, integrate 1 over x dx, so you get logarithm of absolute x. Then don't forget to plus c. So now this is your general solution in terms of x and v, and now you have to convert back to y. So because v equal to y over x, because you start from y equal to v times x, that means v equal to y over x, right? So you substitute it back here. So you get 1 over y over x equal to logarithm of absolute x plus c. And then once you simplify it, so a general solution for this differential equation is y equal to x over logarithm of absolute x plus c. You just simplify it, and this is your final answer. Let's do example 6. So find the general solution of xy prime equal to y times log y over x. Again, I change the question here because the one that I post online in my lecture note, that one is way too long. So I switch it to the better one. This is more compact. So let's start by simplify this thing into the standard form. So I have x dy by dx minus y times log y over x equal to 0. And then that thing is x dy minus y log y over x dx equal to 0. Alright, and then once you have this equation, now you can see that this is your m, right? Negative y log y over x, and this is your n, which is just x. So you have m tx ty equal to ty times log ty over tx. So this is just t times y log y over x. So this is actually t times mxy. So this is homogeneous of degree 1. And then you have ntx ty, which is tx, and that is t times nxy. So this is homogeneous of degree 1. So m and n are both homogeneous of degree 1. So this is actually this differential equation is actually a homogeneous differential equation. Then we're gonna make a substitution. So let y equal to v times x. So let's see what happened here. So then we're gonna have dy equal to v dx plus x dv. And as before, we are going to plug in this thing into the original equation and see how it's go. So let's plug this in back into the original equations. So what I'm gonna get is x. So I'm gonna plug in it to this equation. So what I'm gonna get is x times v dx plus x dv minus vx multiply log vx over x, and then dx equal to 0. Alright, simplify it. So I get v times x dx plus x squared dv minus vx log v dx equal to 0. And then now I'm gonna group dx together. So I'm gonna get vx minus vx log v dx, right? So I group everything with x together, and then plus x squared dv equal to 0. And then now you can see that this is separable equation by you just pull out 1x from the first term. So you get x times v minus v log v dx plus x squared dv equal to 0. So you can make it a lot easier by just keep x squared dv on the left, and then you move all the terms to the right hand side. So you're gonna get x times v log v minus v dx, right? And then after that, this thing is dv over v log v minus v, and then on the right hand side you have 1 over x dx. Now you're ready to integrate. To integrate this separable equation, so you can follow this step. So pull out 1 over v first, so you're gonna get dv over v times log v minus 1, and then on the right hand side you have 1 over x dx, and now you integrate on both sides. On the right hand side this is easy because you integrate, you're gonna get log absolute x, but on the left hand side, so this thing can be integrated by using just u substitution. So you're gonna get integrate 1 over v times log v minus 1, and then you change dv to d log v minus 1, right? And then on the denominator you have to differentiate log v minus 1, so you get 1 over v, and then that thing is integrate 1 over x dx. Just keep it first, and then now you can see that you have something to cancel, and then that is integrate 1 over u du, so that thing is log of log v minus 1, and then okay, absolute value here, and then equal to log absolute value of x plus c. Alright, and that thing is your general solution. So log absolute value of log y over x minus 1 equal to log absolute value of x plus c. This is your general solution, and that is the answer for this question. Alright, let's do this example. Example 7, find the specific solution of this differential equation where y2 equal to pi. Alright, we're gonna assume that we already know that this thing is a homogeneous differential equation. So for now, I trust that every student can check the homogeneous differential equation, so I'm gonna skip that part. If you wanna check that this thing is homogeneous, just let this thing to be mxy and let the second thing here to be nxy, and then you can show that m and n are both homogeneous of degree 1 by using the definition of homogeneous function. So let's skip that part. And then let's start by doing a substitution. Let y equal to v times x. Then now you have dy equal to v dx plus x dv. And then now you substitute back into the original equation. So you have x times sine vx over x minus y times cosine vx over x. And then everything multiply dx, and then plus x cosine vx over x, and then multiply v dx plus x dv. Alright, I think I forgot to change y here to be vx, so let's change this to be vx too. Alright, that looks good. The next thing is I'm gonna expand this thing, so I have x sine v dx minus vx cosine v dx, and then plus, so this thing I'm gonna expand it. So let's start by expand v dx to this parenthesis and x dv to this parenthesis later. So here I'm gonna have v times x cosine v dx, and then plus x squared cosine v dv equal to 0. Alright, and then you can see that the second term here and the third term here, they cancel each other. So what you have left is you're gonna have x squared cosine v dv equal to minus x sine v dx. And then I'm going to move everything in terms of v to the left hand side, move everything in terms of x to the right hand side. So I have cotangent of v dv equal to negative 1 over x dx. Now we are ready to integrate on both sides. So integrate it. So integrate cotangent v dv, you get logarithm of absolute sine v. And then on the right hand side, integrate negative 1 over x dx. So you have negative log absolute x plus c. And then now if you switch v back into y over x, so you have logarithm of absolute sine y over x equal to negative log absolute x plus c. So this is your general solution. All right, we are halfway now, so we have this as our general solution. So in order to find the specific solution, so we have to use the initial condition. So our initial condition is y2 equal to pi. So this means when x equal to 2, y equal to pi. So let's do it. So we're gonna substitute x equal to 2 and y equal to pi, so we can solve for c. Alright, here we have logarithm of absolute sine pi over 2 equal to negative log absolute 2 and then plus c. So sine pi over 2 is 1, so logarithm of 1 is 0. So on the left you have 0. On the right hand side you have negative log 2 plus c. So at the end you have c equal to log 2. So the specific solution is logarithm of absolute sine y over x equal to negative log absolute of x plus log 2. Alright, this is your specific solution, and that is the answer for this question.